Hey everyone, welcome back to Real Analysis 1. This will be part B of lecture 3. Where we left off in part A of this lecture was, well, we had just defined what we mean by an indexed family of subsets, and we completed a number of examples. So we want to kind of continue on with this idea. So the next definition takes index family of subsets and talks about the union of them and the intersection of them. So let's suppose that we have E sub alpha, where alpha is in some index set A. And this is going to be an index family of subsets of X. So it's an indexed family of subsets of some set X. Then we can define the union and we can define the intersection. Okay, so the union of the family of sets we could define like this. It's going to be the union of alpha in A of E of alpha, and that's going to be equal to all of the X in the set X such that X is in E sub alpha for some alpha in A. Okay, just kind of as you'd expect. And we would say that the intersection is the intersection symbol here of the alpha in A of E of alpha. That's equal to all of the X in X such that X is in E of alpha for all alpha in A. Okay. Okay, and so then this allows us to do kind of some interesting things, and let's see some examples here. So for example, let's go back to the example we've been running with, this n sub n. So we'll let n sub n equal 1, 2, dot, 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 up to n. Then we have what? Well, what's the intersection of n sub n? Right, if I take the intersection of n sub n, well, think about what that is. That's all of the elements that are in n sub 1. So you can think of it like this. Right, so it's all of the elements that are in all of these subsets. Well, what element is in all of these subsets? Well, remember the first set is just 1. The second set is 1 and 2, right? So this is just 1. This is 1 and 2. This is 1, 2, dot, 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 up to n. What's the intersection got to be? Well, it's just 1, isn't it? Okay, so the intersection of n sub n, this index subsets of the natural numbers, is just 1. What about the union? Well, you can think of this as n sub 1 or n sub 2 or n sub n. Right, and what is that? Well, remember, this is 1 and 2, this is 1 through n, this is 1 through n plus 1, right? So this is going to equal everything, isn't it? So everything is captured by the union. All right. Very good. All right. Let's do another example here. Right. So here the intersection is this the singleton. The union is everything. It kind of makes sense, right? Hopefully. Let's let n be a natural number and define I sub n as before. This is going to be all of the real numbers x and r such that 0 is less than x less than 1 over n. Okay, what's the intersection here? Well, so let's think about what happened. What do these sets look like here? So the first set, we might say for n equals 1 would be the real numbers in the interval from 0 up to 1. and this would be set 1. All right, what's the second set look like? It's all of the real numbers between 0 and 1 over 2. And then it's 0 to 1/3, and so on. Right, you've got 0 to 1 over n. This continues on, doesn't it? Okay, so what's in the intersection and what's in the union here? Okay, let me flip my page here. So let's start with the intersection. So I would say that the intersection from n equals 1 to infinity of I of n is the empty set. But you may not believe that, right? Let's check. Let's see why. Let's see what kind of reasoning produces this. Let's suppose that the intersection is not empty. Let's kind of do a little bit of like an argument from contradiction here. So let's assume that the intersection here is not the empty set. Okay, let's just start with that. We'll say it's not empty. Then there's going to exist some x in R such that x is in I sub n for all n, right? Right, that's the definition of the intersection. So there's going to exist some x in R such that x is in I of n, I sub n, for all n, right? These are all natural numbers, right? And what does that really mean? Well, that means that 0 is less than x, which is less than 1 over n, for all n in n. Right, but this actually contradicts an earlier theorem. This contradicts an earlier theorem. Right, specifically the Archimedean property. Right, remember the Archimedean property the Archimedean property said that if x and y are real numbers and x is greater than 0, then there exists some natural number such that n times x is greater than y. Right, that was the Archimedean property. And so this assumption actually it produces a contradiction when we think about this theorem. Right? So let's think, how does the contradiction arise? Well, all right, since if x since if there exists an x in R such that x is in I sub n for all n in n, then 0 would be less than x, which would be less than 1 over n for all n, right? And that's going to imply, just do a little bit of algebra here, that's going to imply that 0 is less than n times x, which would be less than 1 for all n in n. Okay? But the Archimedean property guarantees that there does exist an n in n such that nx is greater than 1. But the Archimedean property says there exists an n in n such that n times x is greater than 1, right? But this is telling me that there isn't one. Right? So we've got this contradiction. Okay, so the intersection must be empty, right? We have to go back to the assumption that we made that caused the contradiction to arise. So that is the idea that the intersection is not empty. So so the implication here is that n equals 1 to infinity of I sub n is indeed empty. Okay, that's the intersection. All right, what about the union? The union's somewhat easier to see. Right, the union is easier to see. What about the union, n equals 1 to infinity of I sub n? Well, just think about what all of those sets are, right? So you've got the first set, set 1 is all of the x and r such that x is in 0 to 1. Set 2 is all of the x and r such that x is in 0 to 1/2. Right? And so it's very easy to see that you can continue on, right? X, all of the x and r such that x is in 0 to 1 over n. Right? And so on, continuing onward. Right? So it's easy to see that the intersection, or sorry, the union here is the interval 0 to 1. Right? The interval is basically the entire interval from 0 to 1. Open interval actually has to be open, right? Because of the fact that how the set was described. Right? So the union from n equals 1 to infinity of I sub n is equal to basically all of the x and r such that 0 is less than x, which is less than 1, otherwise known as the interval 0 to 1. Okay. All right. Very good. So those are some examples of things you can do with the intersection and the union of index sets, index subsets, index families. And we'll use this continuously throughout the course. I would say, you know, it'll come up in proofs here and there. We'll use it to construct nice examples. We'll see key historical examples that rely on these things. So very important to get that piece level set, right? And don't worry if you're a little shaky on it. It'll, as we start to work with it more and more, it'll become much clearer. Okay, couple theorems. Okay, first the distributive laws. We're not going to prove these. I'm just going to state them. These are the distributive laws for indexed families. I'm just going to state them. The proofs basically follow the same pattern as proofs from earlier in the set theory section. I think it was 1.1 maybe. But I'll just state them here. So if E sub alpha, where alpha is in A, and E are all subsets of a set X, then two things here. We could say that E and the union for alpha and A of E alpha. So I've got an index family over here, index family of subsets of X, E sub alpha, and I've got some other set E, and I'm talking about the intersection here. Right? So I've got the union of the indexed family intersected with this other set E. Well, that's equal to the union from alpha and A of E and E alpha. Okay, so that makes sense, right? E is intersecting a huge union, so it doesn't have to intersect everything, it just has to intersect something, and that's what you're seeing here. And secondarily, kind of flipping all of these things, we've got E or the intersection is equal to the intersection of E or E alpha. Okay, so again, this follows the same pattern as what we saw for distributive laws earlier in the set theory section. We've got something similar for De Morgan's laws. So these are the distributive laws applied to index families of subsets, and we can do the same thing for De Morgan's laws. So this one says if E sub alpha, alpha in A, is a family of subsets of X, then what? Well, the union of alpha in A of E of alpha, complement of that, right? The complement of the union of this indexed family is equal to the intersection of the complements of the index family, the individual complements of the index subsets. Okay, so the complement of the union is equal to the intersection of the complements. Okay, and then sort of similarly, if I have the intersection of the index family, and I take the complement of that, then that's equal to the union of the complements. Right, so it follows very explicitly the pattern of De Morgan's laws from regular old set theory. Right, and naturally it should, right? That's called the De Morgan's laws. We're applying them here in the case of index families. All right. Very good. Very good. Okay, now we need to talk, I would take this idea of the index family of subsets and extend it into this idea of the image of a function. Right, so a quick theorem here, and this one will prove just because the method of proof is a little more complex, but we want to talk it through a little bit. So let's let f be a function from x into y. Then a couple of things, right? So if E sub alpha, alpha in A, is a family of subsets of x, then the function, so f of the union, is equal to the union of each of the members of the family evaluated under f. Right? So f, if I evaluate the entire union of the index family subsets, it's equal to the union of the individual subsets evaluated under f. Right? And f of the intersection of E of alpha is equal to the intersection of f of E of alpha. Okay, and so those two are things we've seen. We've seen these definitely before. Actually, you know what? I think I have this wrong. I think this should be like this. Yes, it definitely should be. Yes. My apologies. Right, remember that? Remember from section 1.1 we saw something like this, right? So this is actually a subset. It's not equal. The intersection evaluated under f is a subset of the intersection of the individual subsets evaluated. We saw a great example earlier of why that is true in the case of just like regular sets, right? But it's true here too. Okay, and let's talk about the inverse image as well, right? So similarly, if we'll say B of alpha, alpha in A is a family of subsets of X, then we can do something similar with the inverse, right? So F inverse of the union is equal to the union of F inverse of B alpha. Right? And then the intersection works the same way under the inverse function. So the inverse function evaluated on the entire family, the intersection of the entire family, is indeed equal here to the index or the intersection of alpha and A of each individual subset evaluated under the inverse of f. Okay, now obviously we're not going to prove all of these. I think we'll prove, you know what, in the interest of time, I'm not going to prove any of them. Well, let's prove one direction. Let's just prove this one. We can prove this one. Actually, I was going to prove any. I think I'll prove this one, though, just so you can see the method of proof. Okay. So let's talk through that. So proof. And we'll prove that f of the intersection alpha and a e sub alpha is a subset of the intersection of alpha and a of f of e alpha. Added a parentheses there, not a problem though. So to prove this, we basically have to prove one direction, right? That's why this one is kind of a good one to choose. So let's let y be in f of the intersection alpha and a e alpha. Okay, so meaning we'll let f be in this side here, or sorry, we'll let y be an element in this side in this set here. Okay, so then by definition of the image of a set, right? Just by definition of the image of a set, y equals f of x for some x in what? Well, x has got to come from this set here, right? So some x in the intersection alpha and a e sub alpha, right? Well, if x is in the intersection alpha and a of e sub alpha, then x is in e of alpha for all alpha in a, right? That's what the intersection means. And this is going to imply then that f of x is in f of e sub alpha for all alpha in a, right? And, well, that implies then that y is in the intersection alpha and a of f of e of alpha, right? So we started with a y over here, and we've shown that if y is over here, it is necessarily over here as well. So that means that f of the intersection alpha and a e sub alpha is a subset of the intersection of alpha and a f of e sub alpha, which is what we were trying to prove, right? Now all of them kind of follow the same pattern, right? And so I'll leave it to you to prove the remaining ones. Okay. All right. So this is a lot of background, a lot of background. So we're next going to turn, but it can't. I know it may seem like we're kind of jumping around a little bit, but we've got a level set. We've got a certain number of sections that we can work with up front. We have to get a lot of terminology down. Things will sort of level out here in a moment, actually when we move into the next section 2.1. But I want to kind of jump back now to the question of countability, right? So we've got a lot. We started with countability, kind of a motivator. Then we talked about how the natural numbers are countable, how the squares of the natural numbers are countable, how the integers are countable. I want to next talk about how Q is countable. So we'll next turn to the countability of Q. Okay. Now, in order to prove that the rational numbers are countable, we need to use this index family of subsets business, and we also need to use the following theorem. Okay, so this theorem says that if e sub n from n equals 1 to infinity, these are natural numbers, if this is a sequence, this is a sequence of countable sets, right? So if E sub n is a sequence of countable sets and S is equal to the union of E sub n, then S must be countable. Okay. Right, so this is kind of a more general statement than this statement here, obviously, right? But what this is going to do is lay the groundwork for just being able to basically show in one line that Q must be countable, right? If this is going to be used as part of the construction of the countability of Q, right? And so you can see obviously all of the old concepts that we just talked about coming into this theorem, right? We've got, first of all, an indexed subset here. We've got the union of a sequence of countable sets, an index set, right? So we've got kind of both of those ideas, and so we obviously had to define those and work through some examples and develop some intuition on those concepts before we can start using them in theorems, right? But let's go ahead and prove this. Okay, let's prove this one. Okay. So we'll start with the fact that En is countable, right? So since E sub n is countable, right, by assumption here, for each n and n, right? That's an assumption, right? E sub n is a sequence of countable sets, right? So we assume that to be true. So since E sub n is countable for each n and n, we can write E sub n equals x n comma k, x sub n comma k, such that k equals 1, 2, dot, 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 right? And so this is going to be like an enumeration of E sub n. Right, now notice this is for like a fixed n, right? You'd have to make another one for another n, right? But this is for a fixed n, you could write all of the elements out as an enumeration like this. Okay. Okay, let me flip pages here. Since E sub 1 is an infinite subset of S, so E sub 1 is an infinite subset of S, the set S must itself be infinite. Okay, establishing that. Now let's consider the function H that's going to map from n cross n to S. Okay, consider this function, and it's going to be given by h of nk equals x of n sub k, x of n sub k, or n sub nk. Nk is the subscript. Okay. Now the function h is a mapping. It's a mapping of n cross n onto S. Okay, it's not necessarily one-to-one, but it is certainly onto, right? H of n comma k is definitely going, I mean, remember, n and k are both from natural numbers, so everything in S is mapped to here. Remember, we have an enumeration of S here. All right, so H is a mapping of n cross n onto S, right? It's onto S. Now, it's not necessarily one-to-one. We'll see if that matters, though. Okay, but what do we know here? What do we know about n cross n? Well, we already saw earlier that n cross n is equivalent to n, right? Okay, and now we see that an onto function between n cross n and S exists. And so that means n cross n is equivalent to S as well. So these are equivalence relations, right? So you get n cross n is, or n is equivalent to n cross n is equivalent to S, and so the implication here is that n is equivalent to S. Right? So there must exist a mapping from n onto S. There must exist a mapping from n onto S. Okay. And so that means that S is countable, right? At most, it's countable. Okay, and that's what we need, right? So if we have a sequence of countable sets, right, then, and if you've got some subset or some set S that's the union of all of that sequence, then this union must also be countable, right? So the union of countable sets is countable. Is basically the idea here. The idea here is that the union of countable sets is countable. Okay? All right. Now, one of the big theorems here, the rational numbers are countable. Q is countable, right? So the rational numbers are countable. Well, we've already seen that the integers are countable. We've seen that n cross n is countable. In a lot of ways, Q is like those. It's like them in the sense that there's like, you know, when we're talking about rational numbers, we're not just talking about a single integer or a single natural number. We're talking about a ratio of them, right? So it's similar to, I mean, at least from an outside perspective, like when you look at the way those numbers look, you may think that it kind of fits in with some of these other ideas like n cross n, for example, or like the integers kind of. The proof is actually going to be quite different, however. So what are we going to do to prove this? Well, we're going to use the previous theorem heavily. So for each m natural number, let's let E sub m equal the set n over m such that n is in the integers. Okay, so we're fixing m, right, and creating a subset, right, basically a subset of q, right? So we fix m, and that becomes the denominator of every number, every element in this set E sub m, right? So for example, if m is 2, then all of the rational numbers that have 2 as the denominator are going to be in this set. Okay. Now, what can we say about E sub m? Well, E sub m is countable. How do we know it's countable? Well, we can clearly map this onto the natural numbers. I think it's easier to see that it can be mapped to the integers. It can be easily mapped to z. Right, basically the denominator's fixed and the numerator just goes from negative infinity to positive infinity of the integers. Right, so basically f of n is equal to n over m, where n is an integer. Right, that creates a one-to-one onto mapping here. Okay, so we know that E sub m is equivalent to the integers, and the integers are equivalent to the natural numbers, so then by the transitive property of the equivalence relation, E sub m is equivalent to the natural numbers. Okay, all right, so we've got that this singleton set is equivalent to the natural number, so this guy's countable, which we said here, right? So we've got a countable subset of the rational numbers. Well, let's notice that Q, what is Q? Q is all the rational numbers. Well, Q is, oh, hold on. It's all the rational numbers, and Q is equal to the, it's just the union of all of these E sub m's, isn't it? Just the union. And right now keep in mind that m, the denominator doesn't have to range over the negative numbers here, right? So don't be troubled by that. right? Because the numerator is all positive and negative integers, so the denominator can just stay positive and you get all of the positive and negative rational numbers through the numerator, right? So don't let that bother you. So, but notice here that Q is just the union of all such E sub m subsets, and therefore, by the previous theorem, Q is countable, right? Because Q is just the union of countable subsets, right? And we just saw that a union of countable subsets is countable, right? So Q is countable. We can obviously write Q as the union of such E sub m subsets, and therefore it's countable, right? So very easy to prove once you have that previous theorem. All right, very good. Okay, now hopefully you're still a little bit fresh, because here's where things get really wild. Right, so we obviously have this idea of an uncountable set being an infinite set that is not countable, but as of yet we have not seen an example of such a thing. Well, we'll just go forward with the most famous example, and the famous example is that the real numbers are uncountable. Okay, so the real numbers are uncountable. Now the proof of this we'll go through in a second. It's a very famous proof, and it was given by Cantor in, I believe, late 1800s, 1870 something, I believe. And it's called, the proof he came up with is called the diagonal argument, diagonalization proof, something to do with diagonal. It's the diagonalization argument as far as I know. And it's going to be, it is one of the most famous proofs in all of mathematics. It's extremely elegant. It proves something very profound in a very simple way that you could explain. You could almost explain this to people who don't have a mathematics background. They could almost follow the argument. They get a sense for it anyways. And so let's go ahead and prove it. So we'll state the theorem. Right, and the way that we get to R being uncountable, we kind of make it easy on ourselves, and we just start by showing that a subset of the real numbers is uncountable, and by extension, all of the real numbers are uncountable. Right, so what we say is frequently, it can be proven in a number of ways, or there's variations, but this is the one that I think is the best. The closed interval. The closed interval 0 to 1 of real numbers is uncountable, right? So meaning it's infinite and not countable, right? There are more of them than there are natural numbers. Okay, so that's the theorem. Let's prove this theorem. Okay, we know this. We know that this interval is infinite, right? How do we know that it's infinite? Well, we know that it's infinite because there are infinitely many rational numbers between 0 and 1, right? We know that for a fact, right? So we know that this is an infinite interval or an infinite subset because we know that there are infinitely many rational numbers in here. Not even to speak of all of the real numbers that are not rational numbers, all the irrational numbers, right? But we know that it's infinite, and so it's either countable or uncountable. Right, so we'll just kind of summarize that. 0 to 1 is clearly infinite. So it is either countable or uncountable. Okay, so it's either countable or uncountable. Now, to prove that it's uncountable, we need only show that it is not countable. Right? If it's infinite, it's either countable or uncountable. We'll show that it's not countable, so therefore it must be countable. Now, how are we going to do this? To accomplish this, we're going to show that every countable subset of 0, 1 is necessarily a proper subset. Right? We will show that every that every countable subset of 0, 1 is a proper subset of 0, 1, right? So what's the implication there, right? If I can show you that every countable subset of a set is a proper subset, then what I've shown is that I can't get everything in any countable subset, right? So therefore, I cannot capture all of 0, 1 in any countable subset, right? So that's the idea, right? Here's the idea, right? So I mean, it's very important to set the parameters of this proof, right? So 0, 1 is clearly infinite, so it'll either be countable or uncountable. We'll show that it is not countable, thereby implying that it must be uncountable. And in order to show that it's not countable, what we'll do is we'll show that every subset of 0, 1 that is countable is a proper subset of 0, 1, meaning I haven't gotten them all, right? So the only way to get them all is to talk about an uncountable subset, right? So I cannot capture all of 0, 1 in any countable subset. That's the real idea here. Okay, so let's go ahead and get to the meat of it. Okay, so the meat of this argument. we're gonna let E equal the set x sub n such that n is equal to 1, 2, ... Right, so E is going to be an enumeration of, well, no, sorry, not precisely. We're going to let E be the set of x sub n such that n is equal to 1, 2, and this is going to be an enumeration of a countable subset of 0, 1. Right, clearly countable, right, because I'm literally enumerating them. X sub 1, x sub 2, right? So I'm saying everything in E can be paired up with a natural number. So by the implication here is that E is countable, right? And I'm actually just saying that, I'm not merely implying it, but right, hopefully you can see how the way I've said this implies that it's countable, even if I didn't say it, right? And so we're talking about real numbers here. So each x of n, right, each x of n is going to have a decimal expansion. Right, we know this, just basic, basic real numbers 101, right? So each x of n can be written as 0. We'll say xn1, xn2, xn3, xn4, ... right? Right, so what do I mean by this? Well, for example, you would have something like 0.123 4, 5, ... 0.16783, ... 0.99999, ... right? So here's your xn1s, here's your xn2s, here's your xn3s, xn4s, xn5s, right? So for example, right? Okay, so you've got this set of, this countable subset of 0, 1, and everything in the subset can be, we could think of it as having this kind of infinite decimal expansion since these are real numbers. Now, each of these xni's, we'll say where for each k in n, x and k is a digit, right? It's a 0, 1 through 9. Right, just basically saying that these are all digits, single digits, 0 through 9. Right, so for example, 0.1, 1 is in here, 2 is in here, 3 is in here, and so on. Okay. All right, so we've got this list of numbers. Okay, and we can kind of write it out as a list too. I think sometimes that when you're working through these proofs, it's sometimes convenient to write it out as a list just because it helps you to see kind of what's happening here. So maybe x1 is equal to point x11, x12, x13, x14, and so on. X2 is equal to point x21, x22, x23, x24, and so on. X3 is point x31, x32, x33, x34, and so on. And I'll just put one more. This is x4 is equal to 0 point, 0 point, 0 point, 0 point, 0 point, x41, x42, x43, x44, and so on, right? These are infinite decimal expansions. There's infinitely many, but the fact that it's countable means I can enumerate it like this. I can put it in a list, okay? All right, very good. Now, what we're going to do is we're going to define a new number. Okay, so let's define a new number, right? And we're gonna define the number, and it's gonna be y equals 0.y1, y2, y3, y4, and so on, right? Another real number, right? And how are we going to define it? Well, we're going to define it as if x and n is less than or equal to 5, then yn we're going to set equal to 6. And if x and n is greater than or equal to 6, then we'll set yn equal to 3. Okay, now think about what this definition is doing, right? Now notice the nth term of y is defined based on the value of the nth number in the list and the nth digit of that number. So the nth digit of y is defined based on the nth digit of the nth number in our list. Okay, right? And specifically, if that digit is less than or equal to 5, we change our y value to be something bigger. We'll say 6 in this example. But if our nth digit of our nth number is greater than or equal to 6, we'll change our nth digit of y to be 3, something less than 6. Okay, thereby guaranteeing that the nth digit of our y is not equal to the nn digit in our list. Okay, and that's why we sometimes refer to this as the diagonalization arguments. Our value of y is based on the value of this guy, and this guy, this guy, this guy, and so on down to infinity, right? All of them. Okay, so we can define this number y based on our list. All right, what can we say about y? Well, certainly y is in the interval 0 to 1, right? Just look, y is equal to 0 point, da 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 da. It's definitely between 0 and 1. Okay. All right. And so y is in the interval of interest here, but is y part of our countable subset? Is y in E? Well, the answer to that has to be no. No, y is not in E. Specifically, because there is no number in E that has the same value for all n, well, so for all digits in the expansion. Okay, so there's no value, there's no number in E that has the same value for all of the digits in the decimal expansion of y. And specifically, we've made it that way, right? We've said, hey, let's make our y dependent on every number in the list, and let's make it different from every other number on the list, right? So specifically, we know that y is different than x1, at least in this term, right, or this digit. And we know that y is different from x2 specifically because of this digit. We know that y can't be equal to x3 because it has a different third digit, right? It may have other digits that differ as well, but we know for sure that these digits are all different. The first digit is different from x1, the second digit is different from x2, the third digit is different from x3. And so in order for it to be equal to any one of these numbers, it has to have all of the digits the same. And we've just guaranteed that it has at least one digit out of place for every list in this infinite list of numbers. Okay? Right, so what can we say? Then for each n in n, right, for each n in n, y sub n is not equal to x nn, right? And that implies, right, so the nth digit of y is not equal to the nn digit of x, okay? And that implies that y is not equal to xn for any n, okay? And that implies that y is not in E. And of course, the implication there is that E is a proper subset of 0, 1. Okay, now this is certainly going to be true for any countable subset of 0, 1. E was just a generic example of a countable subset. Any countable subset will have this exact same property. Namely, we will be able to enumerate all of the elements of the countable subset, and we can always find some element in the interval 0 to 1 that is not on our list. Right? So the implication ultimately is that 0, 1 is not countable, and therefore 0, 1 is uncountable, and therefore R is uncountable. This is just a tiny little interval of R, which can't even be counted. So clearly, every interval will have the same property. It doesn't matter if we're talking about 0, 1 or 1 to 2 or 0 to 10 or whatever. They're all going to be the same. They're all going to be uncountable, and therefore R is uncountable. And even if they weren't all uncountable, if you have an uncountable section of an infinite subset, it's still uncountable, right? Okay. So that is the famous diagonalization proof of the fact that the real numbers are uncountable. So R somehow has more elements than other infinite sets, like the rationals and the natural numbers and the integers. I mean, as paradoxical and bizarre as it sounds, the rational numbers, the integers, and the natural numbers all have the same cardinality. They all are countably infinite, right? I know that even that is a crazy idea, but now we've shown that there do exist sets that somehow have more elements than other infinite sets. So there's like this hierarchy of sizes of infinity. Right? So we've seen two of them, right? We've seen countably infinite and uncountably infinite now. Okay, and just take a moment to think about how bizarre this is, how unusual this idea is. There are more real numbers between 0 and 1 than there are rational numbers between negative infinity and positive infinity. Right? So that tells you something about how special the real numbers are relative to some of these other number sets. Okay. All right. I think that's a great place to leave off. There are other examples of sets that are uncountable. Real numbers are not the only example. but it is, of all of the numbers we've studied, you know, you've got the natural numbers, the integers, the rational numbers, and the real numbers. There is a clear delineation between the rationals and the reals that this countable versus uncountable draws out. Now, keep in mind also that the real numbers have this least upper bound property, which obviously there's clearly a connection between countable and uncountable infinity and this least upper bound property. Now, as we go further up the list, if we move into the complex numbers are also uncountable, right? Because they're like the real numbers except extended in different dimensions. And so on. As we move up the list, we may see that there are even more types of infinity, right? Indeed, like that was one of Cantor's big hypotheses, was that there was an infinite hierarchy of these different levels of these different degrees of infinity. Okay, so anyways, we'll leave, that's getting into some serious speculation. We'll leave it there for now, and when we come back next time, we'll be getting into we'll start talking about sequences, and so we'll start to nail down some of the foundations of the material we would have covered in a calculus course. So, all right, we'll leave it there. Take care, and we'll talk to you all next time. Take care.